Okay, in this video we're looking at planes. So when you're dealing with a zero-dimensional object, that's a point. If you're dealing with a one-dimensional object, that's a line. And if you're dealing with a two-dimensional object, that is a plane. Sort of looks like a sheet of paper. It just sort of extends out infinitely in all directions. So it's a natural extension of what we've been doing up till now. So let's consider this situation where y equals 2, and we think about all the points which could work for this. 0, 2, 0 certainly works as an option there, and we'll just put that on our little diagram there. 2. We can think of a whole bunch of points. So 1, 2, 0 also satisfies y equals 2, right? It's a little bit silly, the process we're doing here, but you can think of like heaps of different points. 5, 2, 0 would also work. So you could have this point sort of down here at x equals 5. You could have 1, 2, 1. So in that case, you'd sort of be going out to 1 and then up a little bit. So you'd be having that point up there. And if I didn't spoil it for you before, this shape is going to make a plane. You could have anything, 784, 2, and -12, or something like that. But basically, if you sort of plot in all these points, you will sort of get this line there, and then it'll also extend up in the z-axis, and you'll end up making this wonderful, wonderful plane shape. Like a sheet of paper, it extends out forever. Now, GeoGebra 3D can graph these for us as well. That's what it looks like, y equals 2. So the angle we had on ours just there sort of look like that. And you can see from various different angles there, we've got a wonderful plane. Now, in general, plane equations do look a little bit more complex than that. So they've got an x, a y, and a z piece, and they equal a constant. So the general formula looks like ax plus by plus cz equals d. And by letting a, b, and c vary, you get planes at all sorts of wild and wonderful angles. Our equation that we had in this first example happened to have a is 0, b is 1, c is 0, d is 2. Now, importantly, you can actually pull out the normal vector from the plane. By normal vector, I mean the vector which is perpendicular to the plane, or right angles to the plane. So that was the equation of our plane here for y equals 2. That's just a very fancy way of writing y equals 2. And so the normal vector to the plane is 0, 1, 0. So that's just these three coefficients there. Now, what does it mean for a vector to be normal? It means that it's perpendicular. So if I look at this vector, just pick any point on the plane, like here, for example, and I draw the vector coming out from there. That vector is like parallel with the y-axis. That will make a right angle to the plane. And no matter what point I pick on the plane, we're always going to get sort of a right angle there. And planes can be pretty much defined completely by a normal vector and a point which is on the plane. So for example, here's a different plane. Find the equation which has that normal vector and passes through that point over there. So we start off by saying the equation is 1x plus 3y plus 2z is some constant d that we don't know yet. And then we can plug in the point. So x was 9, y was 0, z was 1. So you're going to get 9 plus 3 lots of 0 plus 2 lots of 1 is d. So therefore 11 is d. Therefore x plus 3y plus 2z is 11 is an equation of the plane. X, 3y, 2z, and 11. So we'll just pop that in. And we'll turn off our original plane. So that was the plane we just sort of found there. It's at a wacky angle. And if we look at our original point, 901, that should lie on the plane. So there it is. It doesn't look like it because of the way that it's drawn, but if I sort of zoom out, you can see the plane will extend, and that point A is on the plane. It's like sitting on that sheet of paper there. Now that's what we call the Cartesian form of the plane here. We also have a different version called the vector form. So Vector form is easier to find, but it tends to be used a little bit less than Cartesian form. But it is important to know both methods. Just more often than not, when you're asked for a plane equation, they want it in Cartesian form. To get vector form, we need the position vector and two direction vectors of the plane. Really important that those direction vectors are not parallel to each other, but apart from that, we should be all good. Now, if you've got 3 points, it's easiest to take the position vector as just being essentially the point A, so that's 1, 0, 2. And the two direction vectors could be AB, so that would be a direction vector in the plane, AB there, and the other one could be AC. Okay, we can find AB and AC, so that is 0, minus 3, 1, and AC is going to be minus 1, 2, 3. And the way that I've got that is, how do I get from A to B, and how do I get from A to C? All right, now all we do to get the vector form is just this. So we've got to take, I'm going to do it with vertical vectors just to be a little bit fancy. So t, and then 0, minus 3, 1. So t is just a parameter which can vary freely. In fact, t basically moves you up and down this line here. And then we're going to have another parameter, s, which moves you up and down that line. So s, lots of minus 1, 2, and 3. If you want, you can smoosh this all into one big vector. So you could have 1 plus 0t, take s. You could have 0, take 3t plus 2s. And you could have 2 plus 1 lot of t plus 3 lots of s. And that would in general be the vector form that we're looking for. So we can actually generate some points on here. So if we look at t equals 0, s equals 0 from this thing here, you're going to get the point spit out 102, which was that point that we started with A. If I want to get B or C, so to get B, I could set t equal to 1, s equal to 0. If you work through the algebra of this stuff, you'll end up getting, let's see, 1, minus 3, and 3, which is that point B. And if you want to set t equal to 0, s equal to 1, you can get, so 1 take 1 is 0, you got 2 there, and then you got 5 there, so that would be the point C. You can also generate more points than compared to what was originally on the plane. So you could generate another point here. You could pick any t or s value you want, any real numbers. But you could go t equals 1 and then s equals 1 if you want. And if you look at this, you'll get 1 take s, so that's 0. You get minus 1 for the second term, and then you'll get 6 for the third term. So yeah, 0, minus 1, 6 lies on the plane. And fun fact, just in case you're wondering where that is, it's like there, sort of makes a parallelogram. And you can get any point you want on the plane with this, and A, B, and C sort of make this lovely plane shape with all 3 of them in it. Okay, this is the same plane for this question. It's the same 3 points, but we're going to find the plane in Cartesian form now instead. So for Cartesian form, we need a point and a normal. Now, in the previous question we had the normal and the point just given to us, but now we actually sort of have to find that. So we're going to have the same diagram here. So A, B, and C. To get our point, it's actually pretty easy. It's just 102. Actually, I'll just leave that in point form. So the point is A102. And you can use any of the 3 points you want. It doesn't matter which 3 you use. In fact, I'd recommend picking whatever point has the easiest numbers in it. Like lots of zeros are good, and A has lots of zeros and small numbers, so that's good. We need the normal vector though. So we need a vector, which if this is the plane here, we'd really like our vector to be at right angles to the plane at any point. And in fact, we'd like it to be at right angles to this point in particular. You might be wondering, how the heck do we find that? It sounds like a very complicated problem. Well, conveniently, we learnt a tool for finding that just a couple of videos ago. It's called the cross product. So this normal vector, we can cross together AB with AC. The cross product finds a vector which is perpendicular to AB and it's perpendicular to AC. It's perpendicular to both of those, so it'll be perpendicular or at right angles to the plane. So let's do that. We have AB and AC from before, so 0, minus 3, 1. And AC was minus 1, 2, 3. And then we can just work out what that cross product is. Okay, so that's going to be I with that, minus J, don't forget the minus, 0, 1, minus 1, 3, and then plus K, 0, minus 3, minus 1, 2. So that is minus 9 plus 2. No, it's not plus 2, it's take 2 because there's a take in the determinant formula. It is take J, and we're going to have 0, take minus 1, and then we're going to have plus K, which is 0. 3 minuses give you a minus, so that's minus 3. So you're going to get minus 11I take J take 3K. Just like that. Now, this is our normal vector. If you got a normal vector which was like something like 5, 10, and 20, you're actually allowed to scale that normal vector down. So you could times everything by a quarter and use the normal vector 1, 2, 4. So you are absolutely allowed to do that when you do plane normals. Our normal vector is, we can't really scale it down. But what we can do is we can times everything by minus 1 and make our normal vector look a lot nicer. So positive 11, positive 1, and positive 3. So just be aware that that works. And that means that there are infinitely many different equations for planes. So for example, with this plane that we worked up here, something like 2x plus 6y plus 4z equals 22 would also be correct for an equation of that plane, and it would give you the same plane. That's just doubling everything. Okay, so we've got our nice normal vector, 11, 1, 3. So we know the equation looks like 11x plus y plus 3z is some constant d. And now we sub in our point, 1, 0, 2 to get that. So A is 1, 0, 2. So we're going to have 11 lots of 1 plus 0 plus 3 lots of 2 is d. So that's 11 plus 6 is d. So d is 17. Therefore, our plane equation is 11x plus y plus 3z is 17. All right, so now we got that plane equation. We can actually have a look on GeoGebra. I've typed all this in. So that's the equation of the plane there. It sketches out this shape. And the points A, B, and C from the question I put on GeoGebra as well. And you can see that they do indeed lie on that plane. The other thing we can do is we can check that point we talked about before. I claimed that if you picked different T and S values at this point, 0, minus 1, 6 would lie on the plane. So we can check that. And what do you know? That extra point does lie on the plane. So that's wonderful news. Okay, last thing we need to do is just examples of checking whether or not points lie on the plane. So we checked using GeoGebra just then whether points lie on the plane, but you can do it algebraically as well. And you're not going to have GeoGebra in an exam, so it's good to know. State the normal vector to this plane. So if you get a question like this, 1, 2, minus 1, it's just the coefficients of x, y, and z. Decide whether that vector lies on the plane. Well, the point lies on the plane. So we can sub it into the equation. So x plus 2y take z equals 5. If I look at the left-hand side of that equation, I'm going to have x is 2 plus 2 lots of 1 take minus 1. which is 5. And the right-hand side of the equation, a little bit boring, but it's just 5, so yes. Okay, decide whether that point lies on the plane. So again, we take the equation. We can look at the left-hand side of the equation. So you're going to get 1 plus 2 lots of 0 plus, well, take 0, which is 1. And then the right-hand side is 5. So the answer here is no.